The subcommittees on space and research and technology will come to order. Without objection, the chair is authorized to declare recesses of the subcommittees at any time. Welcome to today's hearing entitled Astronomy, Astrophysics, and Astrobiology. And now I recognize myself for 5 minutes for an opening statement. The science of astronomy, astrophysics, and astrobiology expands mankind's understanding of the universe. It seeks to answer fundamental questions as to the nature of our universe, our place within it, and whether there is life beyond Earth. NASA has a long history of space-based astrophysics and astronomical science. Since the 1960s, NASA has operated space-based observatories. Among the most famous of these are the Hubble Space Telescope, which has produced some of the clearest images of the universe to date. The Hubble Space Telescope became the first of NASA's 4 great observatories, which aimed to observe the universe over the entire electromagnetic spectrum and would go on to include the Compton Gamma Ray Observatory, the Chandra X-ray Observatory, and the Spitzer Space Telescope. Looking to the future, the James Webb Space Telescope, or JWST, is set to launch in 2018. This will be the most powerful space-based observatory to date and will be used to search for planets outside of our solar system that could harbor life. In my own district at Johnson Space Center in Houston, NASA's historic Chamber A thermal vacuum testing chamber will be used for end-to-end testing of JWST's optics in a simulated cryo-temperature and vacuum space environment. I'm proud to represent the hardworking men and women at the Johnson Space Center who have contributed and are contributing to JWST, our nation's next great space-based observatory. In fiscal year 2016, NASA was appropriated approximately $1.35 billion for astrophysics and astronomy. This investment of our tax dollars funds the operation and development of NASA's space-based observatories and the science that is produced. And while I believe that this is a worthwhile investment, I also have an obligation to ensure that NASA's programs are administered wisely. To that end, this committee continues to closely monitor major NASA programs such as JWST and the Transiting Exoplanet Survey Satellite, or TESS, as JWST and TESS progress through the critical integration and testing phase next year and next. I expect regular updates from NASA on progress made and the information about any potential issues well in advance. The science priorities for NASA's astronomy and astrophysics activities are strongly informed by the National Academy of Sciences decadal surveys. The priorities selected for the decade of 2012 to 2021 is outlined in the New Worlds, New Horizons in Astronomy and Astrophysics decadal survey, were to search for the first celestial bodies created in the universe and seek out nearby Earth-like planets suitable for habitation and advance our understanding of astrophysics and the laws by which the universe operates. We are roughly halfway into the prescribed decadal and look forward to hearing about the progress we've made toward achieving these very goals. Since the 2012 decadal, there have also been numerous scientific achievements that continue to inform NASA's astrophysics and astronomy programs. Perhaps one of the most remarkable achievements of the last several years is the discovery of Earth-like exoplanets orbiting distant suns. A little over two decades ago, the only planets known to mankind were those within our own solar system. In the past decades, scientists have confirmed the existence of nearly 3,000 exoplanets throughout the universe, with at least 8 of these exoplanets being roughly the size of Earth and residing in a habitable range of their stars. This hearing also allows us an opportunity to inform the next decadal survey for astronomy and astrophysics, for which NASA has already initiated studies. Outside organizations have already begun to discuss possibilities as well. And with the aforementioned discoveries of exoplanets and the likely operation of JWST in the coming years, there appears to be many areas ripe for future investigations. It is also important to acknowledge the numerous scientific contributions made by private citizens, amateur astronomers, and non-government organizations. Citizen scientists conduct observations and analysis of vast astronomical data sets. This is a good thing because citizen science enhances public engagement and helps inspire the next generation of young students to pursue careers in astronomy, astrophysics, and astrobiology. I want to thank today's witnesses for joining us as we discuss these very important issues, and I look forward to hearing each of your testimonies. And now, before I recognize the ranking member, I would like to ask unanimous consent to enter into the record 2 letters relevant to the hearing submitted by the Association of Universities for Research in Astronomy and the Arecibo Science Advocacy Partnership. Without objection, I so order. Now I recognize the ranking member, the gentlewoman from Maryland, for an opening statement.
Thank you very much. Good morning, Mr. Chairman. I appreciate that you're holding this hearing this morning on astronomy, astrophysics, and astrobiology. I want to also welcome our distinguished panel of witnesses this morning, and I apologize for our delay. Throughout human history, we've looked to the stars to measure the passage of time, to navigate our ships, and decide when to plant our crops. While the study of the night sky has practical benefits to society, its real value is far less tangible, but not less important. Astronomy opens our eyes. It offers a new way to look at the world. And when Copernicus discovered that the Earth orbits the sun, it started a revolution. And when astronomers discovered that stars are made of the same elements as we are, it deepened our connection to stars and galaxies that are unimaginably far away. The recent explosion in exoplanet discoveries has brought us closer to finding out if life is common or rare throughout the universe. Many fundamental questions remain, and it's our job to ensure that scientists have the tools they need to address them. In February, this committee held a hearing to celebrate and learn more about the first ever detection of gravitational waves. If we learned anything, it's that investing in science, even when there is no foreseeable concrete benefit to society, does indeed pay off. Large telescopes like the James Webb Space Telescope, the Wide Field Infrared Survey Telescope, the Large Synoptic Survey Telescope are critical to the next generation of astronomers. We often express our support for science, technology, engineering, and math education, but those efforts are wasted if we don't make decisions now to ensure the development of researchers, facilities, and missions that will enable them to do their work. Astronomical discoveries resonate with the basic human drive to understand our surroundings. The awe they inspire is perhaps the reason that astronomy is one of the most accessible fields of science to the general public. Astronomy serves as a gateway for students who may not otherwise enter a science discipline. And every year, nearly 400 students receive bachelor's degrees in astronomy. Many students who start out studying astronomy go on to pursue careers in medicine, engineering, and data science. In addition to attracting more students to study science, astronomy inspires members of the public to pay attention and even to participate in astronomy. The Hubble Space Telescope made a huge impact on the public's engagement in astronomy. It is often called the People's Telescope because its beautiful images brought the awe-inspiring sights of the cosmos into classrooms and living rooms around the world. Citizen science has deep roots in astronomy. Amateur astronomers have discovered supernova, comets, and asteroids, and even exoplanets. With the advent of the Internet, an even broader group of the public is now able to contribute to research efforts led by the astronomy community. This morning's hearing will give us a chance to discuss the compelling questions astronomers have dedicated their careers to answering, as well as the programs, facilities, and missions that are necessary to enable their investigation into those questions. We live in an era of multi-messenger astronomy. We can see the universe with light, with particles, and now with gravitational waves. And as we look ahead, we must acknowledge that the measurements that are required to advance future astronomical investigations are rapidly evolving. We need to plan ahead to ensure that development of cutting-edge detectors and analysis software keeps pace with the needs of scientists. We have the chance to speak to the leaders of the astronomy community today and to find out where astronomy is going. And one thing is clear. We in Congress need to provide the resources needed to ensure that all areas of science, including astronomy, can continue to carry out groundbreaking discoveries in the years to come. And again, I'd like to thank our witnesses for being here, and I look forward to your testimony. And I also want to acknowledge by my side today our staff, Sarah Barber, who is a fellow with us and has about 6 weeks, and I told her how lucky she was that as an astronomer she gets to be at this hearing. And so thank you, Mr. Chairman, and I yield back.
Yes, ma'am. Thank you. I'd like to recognize one of my interns out there, a student from Texas A&M University, from my hometown of Woodville, Texas, and that's Miss Sarah Reese. Good to have you, Sarah. That's right. Now I'd like to introduce the chairwoman on the Subcommittee on Research and Technology, Mrs. Comstock, gentlewoman from Virginia.
Thank you, Mr. Chairman, and I also welcome your A&M student. I have family down in Bryan, Texas, so great university there. Since 2000, 7 of the 8 people to receive Nobel Prizes for astrophysics work have been American scientists. The United States has had tremendous achievements in astrophysics and astrobiology research. Taxpayer-supported grants from the National Science Foundation fund much of this groundbreaking research. In fiscal year 2016, NSF will spend over $246 million to support the astronomical sciences. That money goes toward an incredible variety of projects, from funding facilities like the Green Bank Telescope in West Virginia to small research grants given to faculty and students at universities around the country. It has been a productive year for federally funded astrophysics research. The biggest achievement was the detection of gravitational waves at the LIGO Observatory this past September, proving part of Einstein's theory of relativity. Just a couple of weeks ago, LIGO announced a second discovery. This amazing project was able to detect ripples in space-time caused by a collision of black holes 1.3 billion light-years away from fields in Washington and Louisiana. LIGO and its predecessors have been funded by NSF for over 30 years, and its top scientists will almost certainly receive a Nobel Prize. Some of NSF's most interesting astronomy projects are still in the works. The Large Synoptic Survey Telescope, or LSST, will produce an incredibly detailed picture of the full night sky every 3 nights for a decade. It will make its findings available to the public as it goes along, resulting in the world's largest public data set. And I think this is particularly exciting when you look at all these projects and how the public can participate, how all of our online capacity can bring this into every classroom, every part of the country, really every part of the world, wherever there might be some kind of device they can view it on and interact, and that's a really exciting aspect of it. The Daniel Inouye Solar Telescope is another important upcoming project. Scheduled to start operating in 2018 in Hawaii, it will produce the most detailed images of the sun ever by a ground-based device. NSF-funded astronomy programs are among the largest sources of international collaboration for American scientists. In particular, the Gemini Observatory and the Atacama Large Millimeter Array are multinational projects which each involve at least 5 nations. It would not be possible for any of them to accomplish individually. Still, NSF's astronomy program faces questions going forward. The Arecibo Observatory, long one of the premier sites it funds in Puerto Rico, is nearing the end of its life cycle. NSF needs to decide what it will do with the facility, which many in the scientific community believe can still contribute to furthering scientific discoveries and providing education opportunities. It is in our nation's best interest to continue our commitment to researching the fundamental nature of the universe. Breakthroughs like the detection of gravitational waves inspire the next generation of scientists. For the American economy to be successful in the 21st century, we need to have that skilled labor force and workforce that understands innovation and emerging technologies and leads. And I wanted to particularly note today, I'm very pleased to see the balance of women here in our panel. Having passed the Inspire Act here earlier on this committee, it's really exciting. Actually, you're outnumbering the men today, so that's particularly exciting also. So we really look forward to you inspiring the next generation of leaders. And I look forward to hearing from this panel of accomplished witnesses this morning, one of whom directs all astronomical science projects at NSF. So thank you.
Thank you, Chairman Comstock. Now, I'd like to recognize the chairman of our full committee, a gentleman from Texas, Mr. Smith, Chairman Smith.
Thank you, Chairman Babin. The science of astronomy goes back millennia and is one of the oldest of the natural sciences. Astrophysics, the application of physics to understand the nature of the universe, is a relatively new scientific field that has blossomed in the last few years. Space-based observations from telescopes like the Hubble Space Telescope have amazed us for decades, and the James Webb Space Telescope is only a couple of years away from launch. Recently, we have seen amazing discoveries of planets outside our solar system and the detection of gravitational waves. This is just the beginning. Many more amazing discoveries await us. NASA's chief scientist, Dr. Ellen Stofan, recently testified before this committee that, quote, "With future technology and instruments currently under development, we will explore the solar system and beyond, and could indeed, perhaps in as little as 10 to 20 years, discover some form of life, past or present," end quote. Since 1995, over 3,000 exoplanets have been identified, with several found to be in the habitable zone, where a planet with sufficient atmospheric pressure can maintain liquid water on its surface. The Kepler spacecraft discovered many of these exoplanets and led scientists to estimate that as many as 11 billion rocky, Earth-sized exoplanets could be orbiting in the habitable zones of Sun-like stars in our Milky Way galaxy alone. Kepler's successes in hunting exoplanets will continue with the launch of the Transiting Exoplanet Survey satellite in 2017 and be augmented by the capabilities of the James Webb Space Telescope, the Wide Field Infrared Space Telescope, and ground-based telescopes such as the Large Synoptic Survey Telescope, or LST. The LST may be able to peer into the atmospheres of these exoplanets and conduct spectrography to determine the composition of their atmospheres. Well, while partnerships between the private and public sector in astronomy are well established, these ties need to be strengthened when it comes to exoplanet surveys and exploration related to astrobiology. Private sector groups like the Breakthrough Listen Project provide funding opportunities to leverage limited government funding to maximize discovery. Going forward, I hope that NASA, NSF, and academia will expand public-private partnerships to advance optical laser transmission surveys, as it is a promising and exciting field of inquiry. Mr. Chairman, I look forward to our witnesses' testimony today with representation from NASA, the NSF, the Astronomy and Astrophysics Advisory Committee, the American Astronomical Society, and the Breakthrough Listen Project. We have the opportunity to hear a number of perspectives on the subjects of astronomy, astrophysics, and astrobiology. Thank you, and yield back.
Thank you, Mr. Chairman. Now I'd like to recognize the gentlewoman from Maryland for a statement on behalf of Ranking Member Johnson.
Thank you, Mr. Chairman. Just for the record, we've entered the Ranking Member Eddie Bernice Johnson's statement in the record today, and she regrets that she is not able to be here today. She's attending the memorial service in Dallas today. Thank you. Now yield.
Thank you. Now let me introduce our witnesses for the day's hearing. And our first witness today is Dr. Paul Hertz, Director of the Astrophysics Division at NASA. Dr. Hertz is responsible for the agency's research programs and missions necessary to discover how the universe works and explore how the universe began and developed into its present form, and to search for Earth-like planets. Dr. Hertz received a BS degree in both physics and mathematics from MIT, followed by a PhD from Harvard University in astronomy. Our second witness today is Dr. Jim Ulvestad. I hope I pronounced that right. Okay, Ulvestad. Is that it?
Ulvestad.
Ulvestad, okay. Jim Ulvestad, Director of the Division of Astronomical Sciences at NSF. In this role, he leads a staff of 25 and oversees an annual budget of $246 million, plus major observatory construction projects with an additional budget of $100 million in fiscal year 2016. He earned a bachelor's degree in astronomy from the University of California at Los Angeles and a PhD in astronomy from the University of Maryland. Our third witness today is Dr. Angela Olinto, Chair of the Astronomy and Astrophysics Advisory Committee, or AAAC, and Homer J. Livingston Professor in the Department of Astronomy and Astrophysics at the Enrico Fermi Institute at the University of Chicago. Dr. Olinto is the principal investigator of the Extreme Universe Space Observatory on a super-pressure balloon mission and a member of the international collaboration of the Pierre Auger Observatory. She received her Bachelor of Science in Physics from the Pontificia Universidade Católica of Rio de Janeiro in Brazil, and her PhD in Physics from MIT. Our fourth witness is Dr. Shelley Wright, member of the Breakthrough Lesson Advisory Committee and assistant professor at the University of California in San Diego. Dr. Wright has extensive experience working with optical infrared instrumentation with a particular focus on imaging cameras and spectrographs that operate behind adaptive optics systems on large telescopes. She currently serves as project scientist for the First Light Instrument, or IRIS, for the future 30-meter telescope. Dr. Wright received her Bachelor of Science in Physics at the University of California in Santa Cruz and her PhD from UCLA. Our final witness of the day is Dr. Christine Jones, who is president of the American Astronomical Society and senior astrophysicist at the Smithsonian Astrophysical Observatory. Throughout her career, Dr. Jones has worked on a variety of research topics, but most recently her research is focused on X-ray studies of the hot gas in galaxies and galaxy clusters using the Chandra X-ray Observatory. Dr. Jones earned her AB, or MA, and her PhD degrees in astronomy at Harvard University. So thank you all, distinguished witnesses, for being here today. And I now recognize Dr. Hertz for 5 minutes to present his testimony.
Thank you, Mr. Chair. Members of the committee, I am pleased to appear before you to discuss the current and future astrophysics programs at NASA. How did our universe begin and evolve? How did the familiar night sky of galaxies, stars, and planets come to be? And are we alone in the universe? These are the enduring questions that humankind has been asking since we first looked up at the sky. And now, for the first time, we're able to answer those questions scientifically. We're probing back in time with the Hubble Space Telescope, detecting faint infrared signals from galaxies that formed 13 billion years ago, only 400 million years after the Big Bang. Hubble and the Chandra X-ray Observatory are working together to study supermassive black holes, showing how they formed in the early universe and how they triggered the birth of stars and galaxies. And NASA is developing 2 new space observatories to further advance our understanding of the cosmos. The James Webb Space Telescope, which will launch in 2018, will detect the light from the first stars and galaxies that formed after the Big Bang. And the Wide Field Infrared Survey Telescope, or WFIRST, will launch in the mid-2020s and help us understand the mysterious dark energy that is propelling the acceleration of our universe. Understanding the origins of galaxies and stars leads us to an understanding of how planets formed, including planets capable of supporting life. Our knowledge of planets outside of our solar system, exoplanets, has exploded in the last 20 years. Thanks to the pioneering discoveries made with ground-based observatories, followed by the Kepler Space Telescope, we now know that planets orbiting other stars are common. For 4 years, Kepler measured the light from 150,000 stars, staring at them 24 hours a day, 7 days a week, 365 days a year, and discovered at least 5,000 exoplanet candidates around those stars. The exoplanets discovered so far are astounding in their diversity. One is a rocky, hot planet locked by gravity, with one side always facing its star, wild swings in temperature that hint at a surface bubbling with rivers of lava. Another is a scorching alien world where it rains glass sideways with winds of 4,500 miles per hour. And another is half the size of Jupiter but speeds around its star in only 4 days instead of the leisurely 12 years that Jupiter takes to orbit our sun. The Hubble Space Telescope has detected the most distant exoplanet known and has measured the atmospheric composition of many exoplanets using the parent star's light filtered through the exoplanet's atmosphere. And the Spitzer Space Telescope has probed the temperature and atmospheric composition and even weather on distant exoplanets. But the most compelling search is for the rocky planets that, like the Earth, might be capable of supporting life. To date, we have found 9 roughly Earth-sized planets located in the habitable zone of their parent stars. But this type of planet lies at the limits of what we can discover using our current generation of space telescopes. The Webb telescope will examine the makeup of known exoplanets through both transit spectroscopy and direct imaging. And the new observatories coming online will discover new exoplanets for study by Webb. The Transiting Exoplanet Survey Satellite TESS and the previously mentioned WFIRST. Now, one thing that Hubble, Chandra, Spitzer, Webb, and WFIRST all have in common is that they were recommended by a decadal survey. As the time approaches for the next decadal survey, NASA has initiated mission concept studies to inform the next decadal survey's deliberations. Following the recommendations of our advisory groups, we have identified 4 large mission concepts to study. What type of science might we expect from future NASA space observatories? An X-ray surveyor might discover the first generation of supermassive black holes and explain in the early universe and determine the influence of dark matter on the evolution. A far-infrared surveyor might find biosignatures in the atmospheres of exoplanets and explain the origins of the dust and molecules that serve as the prerequisites for life. An ultraviolet visible infrared surveyor with a large mirror might capture the first starlight in the early universe, detect water worlds and biomarkers on distant Earth-like planets, and image the icy plumes from moons of giant planets in our own solar system. And a habitable exoplanet imaging mission might search for signs of habitability in the atmospheres of planets orbiting stars in our Milky Way galaxy. We're fortunate to live during a time when grand scientific quests are possible and in a country that values the curiosity and discovery as inherently noble pursuits. And at NASA, we're thankful to Congress for its continued support. So thank you, and I'll be pleased to take any questions the committee might have.
Thank you, Dr. Hertz. Now I'd like to recognize Dr. Ulvestad for his opening statement.
Thank you, Chairman. Chairman Babin, Ranking Member Edwards, Chairwoman Comstock, Chairman Smith, and members of the subcommittees, we thank you for the opportunity for the National Science Foundation to discuss the exciting progress in astronomy, astrophysics, and astrobiology, and the outlook for the future. This remarkable progress is the product of sustained taxpayer support through representatives such as yourselves and the long-term effort of the basic research community, represented here on my left. For millennia, humans have viewed light from the sky to learn about the universe. Today, we observe across the electromagnetic spectrum from radio waves to gamma rays and are ready to look at the universe in new ways. Particles, such as neutrinos and cosmic rays, provide a different view, and gravitational waves give yet another. In this new era of multi-messenger astrophysics, NSF has a leadership role. The 6th Astronomy and Astrophysics Decadal Survey was delivered in 2010 by the National Academies. The survey stressed the importance of supporting individual investigator research as well as developing forefront observatories. 3 principal science areas were identified: cosmic dawn, searching for the first stars, galaxies, and black holes; new worlds, seeking nearby habitable planets; and physics of the universe, understanding scientific principles. These scientific areas represent enduring human quests. Take new worlds as an example. The Atacama Large Millimeter Submillimeter Array, ALMA, was recently completed by NSF and its international partners. You see before you the recent ALMA image of the star HL Tau, 450 light years away, which shows rings of gas and dust circling the star. The gaps in those rings, indicated by the dashed lines, are swept out by planets, just as Saturn's satellites sweep out gaps in its famous ring system. NSF and NASA are collaborating on a new instrument to measure the velocities of stars precisely and detect motions influenced by planets having masses similar to Earth's. This instrument will be installed on the University and NSF-supported WIND telescope in 2018. Finding and characterizing Earth-like planets is an important step in understanding how planetary systems form and evolve, and ultimately whether they can host life. NSF and its awardees also are constructing 2 major observatories recommended by decadal surveys and funded by Congress. The Daniel K. Inouye Solar Telescope, which you see before you, that's an actual image, not an artist's conception, is being built on the island of Maui. Its observations will provide a deeper understanding of the sun's processes. Those processes lead to the activity that we call space weather, which has the potential to significantly impact communication and navigation systems in space and on the ground, power grids, and astronaut safety. NSF, with DOE and private partners, leads the construction of the Large Synoptic Survey Telescope, LSST. LSST is the highest priority ground-based recommendation of the last decadal survey. It will revolutionize modern astrophysics. LSST will discover thousands of potentially hazardous near-Earth asteroids. It will enable contributions by citizen scientists who will use its data sets to participate in the excitement of astronomical discovery. NSF has also responded to another decadal survey recommendation by initiating a mid-scale innovations program. This initiative is an ideal hands-on training ground for young scientists and instrument builders who will participate in the great observatories of the future. When I left graduate school, we did not know that the expansion of the universe was accelerating, that there were thousands of other solar systems, or that we would detect gravitational waves from merging black holes. Those discoveries relied on many years of support for individual investigators, on spectacular computer simulations, and on frontier observatories. With NSF observatories such as ALMA, the Laser Interferometer Gravitational Wave Observatory, and the IceCube Neutrino Observatory, we are moving rapidly into an era of multi-messenger astrophysics. NSF is proud to work with our many partners and the broad community of scientists. We are poised to continue a journey of discovery on behalf of the American public, and we thank you and all U.S. taxpayers for your support. This concludes my testimony, and I'd be happy to answer any questions.
Thank you very, very much. And now I recognize Dr. Olinto for 5 minutes to present her testimony.
Thank you, Mr. Chairman. Chairman Babin, Chairwoman Comstock, Ranking Member Edwards, Ranking Member Lipinski, I'm not sure he's here, members of the subcommittee, and Chairman Smith. Thank you so much for having us come here today, and it's a pleasure for me to share findings of the Astronomy and Astrophysics Advisory Committee. I'm Angela Olinto, Professor of Astronomy and Astrophysics at the University of Chicago and the current chair of the AAAC, which is a faculty committee of 13 scientists charged to assess the coordination of astronomy and astrophysics programs of the NSF, NASA, and the DOE. And also, we assess the status of the activities relating to the priorities of the decadal surveys of the national academies. Over the last few decades, astronomers and astrophysicists have revolutionized our understanding of the universe, our place in it, and the fundamental laws that govern its evolution and the systems within it. These impressive achievements are a direct result from the long-standing national investment in basic scientific research. I thank the committee and its role in continuing support for basic science. This year, the world celebrated the historic breakthrough of the first observations of gravitational waves by LIGO. This landmark discovery, discussed here in February, demonstrates the power of long-term investment in basic research by the U.S. through the NSF and the ability of scientists worldwide to work together in the challenging and fascinating quest to understand nature. This new window enables direct observations of the most extreme events of our universe, including the earliest moments of the Big Bang. primordial gravitational waves may soon be discovered by the studies of cosmic microwave backgrounds, while a future gravitational wave space mission reached an important milestone this year, the success of the LISA Pathfinder. Gravitational waves add a new dimension to traditional astronomy, which is based on the broad electromagnetic spectrum. Together with cosmic rays and neutrinos, the multi-messenger universe is now observed with frequencies spanning 35 orders of magnitude. If we translate that to music, it is equivalent to a piano with 116 octaves instead of the usual 7, which would be 83 feet piano, twice the size of this room. We need a lot of hands and bright minds to play such an instrument. Astronomy and astrophysics contributes to astrobiology in many areas, most prominently in the study of new worlds or exoplanets, one of the 3 main science themes of the 2010 Decadal Survey. The diversity of the discovered new worlds have surprised us all. They are much more numerous and diverse than the most creative science fiction imagined. An active program to characterize exoplanets, their surfaces and atmospheres, uses both ground and space telescopes. The launch of JWST and TESS in the next 2 years will strengthen the effort further. JWST, the most powerful telescope, as mentioned here before, will be taking spectra of transiting exoplanets, while TESS will be searching for nearby Earth-like planets, providing great targets for JWST. In the next decade, the highest decadal priority, WFIRST, will inaugurate space-based direct imaging in reflected light and pave the way to a future flagship mission that might image Earth-like planets. The AAAC finds the U.S. investment in astronomy and astrophysics continues to support an outstanding portfolio of preeminent research facilities, and the coordination between NSF, NASA, and DOE has been exemplary. These discoveries have captivated the public and inspired new generations of scientists and engineers to continue to expand our knowledge and secure our future leadership in science, technology, and space. However, the AAAC is concerned about the balance of the portfolio. At both NSF and NASA, competed grants and mid-scale programs are being squeezed by flat or declining budgets. These programs form the new generation of scientists and ideas. Success rates have declined in the last decade from 30% to 20%, and this is affecting the morale of the community. As we plan for a future with the U.S. leadership, investment in the next generation of scientists and ideas is crucial. I was born in the U.S. because my father came here to do his PhD before returning to Brazil. 20 years later, I dreamed of doing the same thing. I applied to U.S. Graduate schools in spite of being bad-bound. I was very lucky because I have my health back and also the opportunity given to my generation by those who built the great U.S. research institutions in the past. Since then, I have mentored many students at Chicago who are now following their dreams in academia, national labs, and industry. Of my graduate students, 73% have been women, including the first African American to get a PhD in our department. I would like to ensure that the diverse and brilliant young talent in this country will also have the great opportunities we have. My one message today is to strengthen the base program that needs help after the past years of constrained budgets. Let's support the next generation as past generations have supported us. Thank you for listening. I'll be pleased to answer any questions.
Muito obrigado.
De nada.
Thank you for that. I now recognize Dr. Wright for 5 minutes to present her testimony.
Thank you, Chairman and esteemed committee. Thank you for the opportunity to discuss the scientific pursuit for finding other intelligent life in the universe. I'm an assistant professor in physics at University of California, San Diego. I spend my time teaching astrophysics, researching galaxies, and building new instruments for the world's largest telescopes. I am also one of a few SETI researchers worldwide. The search for extraterrestrial intelligence, SETI, is a scientific pursuit of detecting technological transmissions from other intelligent life in the universe. In particular, SETI searches for a signal purposely sent or accidentally leaked from an advanced civilization. We are in the midst of a dramatic paradigm shift. Only in the last few years, thanks to NASA's successful Kepler mission, we know that 1 in every 5 sun-like stars in our galaxy harbors an Earth-like planet. This greatly encourages our search for life and intelligent life elsewhere in the universe. But given the lack of sustained academic funds for SETI, few opportunities exist for researchers and students to engage in this field. Yet many believe there is no single discovery that will more fundamentally change humankind's view of our place in the universe than to discover ET. Since the search in 1960, SETI is predominantly conducted at radio wavelengths. Numerous SETI programs have made use of the largest U.S. and international radio telescopes. Still, SETI radio searches have barely scratched the surface for detecting faint interstellar signals. Thanks to constantly improving technology, the coming years still promise new, more sensitive SETI searches. Breakthrough Listen, a 10-year, $100 million SETI initiative sparked by philanthropist Yuri Milner, began operations just this year in January. Breakthrough Listen is using the Green Bank Telescope in West Virginia, the Parkes Radio Telescope in Australia, to attempt a radio search that is 50 times more sensitive and covers 10 times more sky than all previous SETI searches before. Just this month, the Chinese have finished final assembly of the world's largest radio dish at 500 meters in diameter. Chinese scientists have slated this dish to be used for very sensitive SETI program, thus adding significant international competition to the SETI field. The radio regime is just one small portion of the electromagnetic spectrum. It has been suggested for decades that other wavelengths may be just as viable for interstellar communication. The discovery of laser technology opened a new realm and offered several advantages over radio. Lasers can be narrowly beamed, thus transmitting power efficiently, and its beam can be packed with more information per energy used. Using our laser technology today, humans would have the capability to transmit a signal that would be easily detectable thousands of light years from Earth, encompassing millions and millions of stars. Our group has constructed SETI instruments at Lick and Leuschner observatories to search for fast-pulsed optical laser signals that have a burst within nanoseconds or shorter. In parallel, a team from Berkeley searches for continuous laser signals using high-resolution spectra from Keck Observatory. Breakthrough Listen also supports an optical SETI program that seeks laser signals and optical spectra at Lick Observatory. But another promising area for SETI is at infrared wavelengths. Infrared detectors have been rapidly improving, only recently making an infrared pulse laser SETI search possible. In fact, sending a laser signal in the infrared is more advantageous because it's less diminished by interstellar dust and gas. Our team designed and constructed the first ever near-infrared SETI experiment. This program has been superb for training undergraduate and graduate students and postdocs. Our team and others are now working to design and seek funding for new SETI experiments. Enthusiasm is ever increasing for SETI, but resources are scarce. A huge disparity exists between the enormous public and scientific interest in whether we are unique in the universe and resources that are actually allocated to SETI research. Since 1977, there's been roughly a flat rate of refereed publications about SETI, with a number of worldwide dedicated SETI research levels at a mere 24. Even with the much-needed catalyst of funds recently provided by private foundations, leveraging private and public sectors is vital for creating a sustainable and growing community of SETI researchers. 2 decades ago, unknowns about astrobiology and extrasolar planets discouraged government funding for SETI. Today, thanks to successful NASA, NSF, and national supported missions, former concerns about the value of SETI research no longer apply. While there's much to learn about the universe, the relevance for advancing SETI is stronger today than ever before in the history of humankind. So thank you for your consideration and listening today.
Thank you, Dr. Wright. Now recognize Dr. Jones for 5 minutes to present her testimony.
So Chairman Babin, Chairman Smith, Ranking Member Edwards, and members of the subcommittee, thank you for the opportunity to testify today on behalf of the American Astronomical Society, the professional society of our discipline in the U.S. We're very fortunate in the U.S. to have a robust fleet of space and ground-based observatories that allow us to make exciting new discoveries about our universe. Congress has long been a strong supporter of these programs at NASA and NSF, and for that, our community is extremely grateful. I hope to give you just a snapshot of the exciting research, technology development, and education and outreach activities that astronomers engage in. As you know from these other testimonies, not very long ago, the only planets we knew about were in our solar system. Dark energy had not been discovered, and supermassive black holes were not known to be common in the centers of galaxies. A lot's changed since then, thanks to significant public and private support. Today, we've discovered almost 3,000 exoplanets and have another 2,500 candidates. NASA's Kepler mission found an exoplanet orbiting two suns, colloquially known as Tatooine, after the double star system in Star Wars. Just last week, a U.S.-led team using a European ground-based telescope announced the discovery of an exoplanet with 3 stars, one better than Tatooine. Thanks to ground and space-based observations, we now know that normal matter, the sort of stuff we deal with directly every day, makes up only a small fraction of the mass in the universe. The rest of the mass is dark matter, or dark energy, which isn't even matter at all, but it is driving the accelerating expansion of the universe. Although as president of the AAS, I speak on behalf of all the astronomical scientists, I'm also an active researcher. My research focuses on the effects supermassive black holes have on their host galaxies. These black holes have occasional very large outbursts that prevent new stars from forming in their galaxy. It's amazing to think that something so relatively small in size has an impact across a galaxy many tens of thousands of light years in size. This research has more than pure academic value. The technology that we develop to explore the universe transfers beyond our field. I want to mention just 2 examples. Much of the time, as you've heard, when astronomers want to study objects, they're very, very faint. They can be distant galaxies, they can be very faint objects in our own solar system. To study such faint astronomical objects, we need both large telescopes and very sensitive instruments. Although the first CCDs were made for data storage devices, astronomers recognized that they could be modified to function as core components of highly sensitive, efficient, and stable imaging devices. Astronomers working with industry and the government helped improve CCD detectors, so they're part of the workhorse of instruments on ground and space-based telescopes. Variations of that technology was transferred beyond astronomy and are now the crucial components of innumerable digital imaging systems, including the camera that you probably have in all of your cell phones. And technology originally developed for observing X-ray sources in space is also used for security screening. The company American Science and Engineering, where Nobel Prize-winning astronomer Riccardo Giacconi worked, also developed and built the first X-ray scanners. Next time you put your bag through the Smithsonian's Air and Space Museum scanner, take a moment to look at the AS&E label that's on the side. But perhaps the most important technology transfer of all is the technically trained people. Astronomy is really a gateway science that brings people into STEM fields, and astronomers love sharing what we do with the public. Undergraduate Astro 101 courses enroll approximately 250,000 students each year nationwide and are taken by about 10% of all college students, making it one of the most popular general education courses. NASA and NSF have very active and successful education and outreach programs. This includes the Hubble program that brings formal science education to students in half of the public middle schools in the U.S. Programs at NSF, like the Research Experiences for Undergraduates, play an important role getting undergraduates from diverse backgrounds exposed to doing forefront research. But even with these programs, most scientific fields, including ours, have a long way to go on the path toward being fully inclusive of underrepresented minorities. There are no easy answers or quick fixes, but our community is committed to doing better with the help of our colleagues at NSF and NASA. In closing, the mission of the AAS is to enhance and share humanity's scientific understanding of the universe, where it came from and where it's going. It's a challenging mission. And what we do resonates with the American people. Discoveries graced the front pages of major newspapers, and people filled Times Square to watch Curiosity land on Mars. The public wants us to uncover more of the mysteries of the universe and to share those results with them. That is what astronomers do, and it is what funding from Congress facilitates. It's a delight to participate in this effort as a researcher, an honor to serve as the president of the AAS, and I look forward to answering your questions here today and in the future. Oh, and I couldn't help but notice that there are 7 members of the full committee from Texas, including Chairman Smith and Ranking Member Johnson, who's not here right now. And it turns out that 2017 is the year of Texas for the AAS. Please accept my personal invitation for you or members of your staff to attend the Society's conferences next year. In January, we'll be in Grapevine. and in June we'll be in Austin. Thank you very much.
Thank you very much, Dr. Jones, and I hope that my scheduler will take note of that, and I'd love to be there. Anyway, we certainly thank all of you witnesses for your testimony, and now the chair recognizes himself for 5 minutes. The JWST thermal vacuum testing will be conducted at the Johnson Space Center's Chamber A, which is the largest high-vacuum cryogenic optical test chamber in the world. Chamber A was famously used for Apollo testing, and Dr. Hertz, if you can speak to how this unique facility supports astronomy and astrophysics missions.
Thank you, Mr. Chair, for that question. One of the lessons that NASA has learned over the years of launching many successful space missions is that a thorough testing on the ground is the key to making sure they work the first time we turn them on in space. Unlike ground-based observatories, we can't send our technicians in to fix them if that turns out to be, if we don't get them working right. Chamber A is the only place in the country where we could do a full end-to-end test of the James Webb Space Telescope. The Webb telescope is being assembled right now at the Goddard Space Flight Center, and early next year we will be shipping it down to Houston to put it into Chamber A, where we will spend a good fraction of the year doing the end-to-end tests with the flight telescope and all 4 flight instruments inside the chamber to make sure they work as a complete system.
Thank you very, very much. And we're looking forward to observing some of these tests. My next question is for Dr. Olinto. One of the reasons the Hubble Space Telescope is so successful is that it could be serviced by the space shuttle. How could a deep space exploration vehicle like Orion impact future astronomy and astrophysics missions? And how would future astronomy and astrophysics missions benefit from being capable of crew servicing if they are reasonably within reach of the SLS and Orion?
Just repeating what Paul just said, it is really important to make sure it works perfectly before you launch, because it's obviously a very difficult thing to do. We are very proud that the Hubble was serviced and it's so capable of doing gorgeous things, including my scarf. But going to, for example, L2 to service JWST will be a much harder job. It's much further away. So I think this is a challenge that I'm sure that if we are willing to spend a lot of money on it, we should be able to do it. But in terms of priorities, I think the best is to make sure it's really working on the ground. So servicing things far away is really challenging. On the other hand, we need to keep those capabilities developing for future missions, which might be become more affordable to go service something in L2, for example. So, and I imagine that for very far away, robotics would be the way to go first, so that we make sure our astronauts come back healthy.
Okay, thank you. Absolutely. Now, a question to really everyone concerning the SLS. How will the capabilities of the Space Launch System impact future astronomy and astrophysics missions? Some of it's been addressed already. And how should the next decadal survey account for these capabilities? Who would like to address that first?
I'll start off, Mr. Chair. The SLS offers a number of capabilities that could be used by future space-based observatories. Primarily, it's the large mass it's capable of launching into space and the large fairing that it will have compared to some of the current generation of launch vehicles. As many of the witnesses have testified, the frontiers of astrophysics require us to image things which are very far away and very faint. That means very large mirrors in order to collect enough light for us to make scientific deductions about what we're looking at. Large mirrors are both large and heavy, and the SLS can help us solve both of those questions. As I mentioned, we have ongoing right now 4 studies of potential future NASA missions to help inform the next decadal survey, and all of those committees are looking at whether, so all those studies will lay out what are the requirements for those future observatories, and if those requirements can be best met by an SLS instead of some other launch vehicle, that is certainly one of the tools that would be available for realizing a future observatory.
Okay, thank you. Anybody else want to take a answer to that?
Just echo that large mirrors are definitely a must for us. The larger, the better.
Okay, well, that completes my line of questioning, and thank you very much. And now I would like to recognize the gentlewoman from Maryland for her questions.
Thank you very much, Mr. Chairman, and thank you so much to the witnesses for your testimony. You just make me so excited just to be here. And I don't do astronomy, but I'm one of those kids that went to the planetarium and lay down on the beach at night looking up at the stars in the sky and wondering what was out there. And so thanks for your testimony today, inspiring new generations. I was recalling with our staff here, we were going back and forth, that both the Hubble Space Telescope and Kepler, both at various times in their development and operation, were on the chopping blocks here in the Congress. There was a time when the Hubble was the butt of late-night jokes every night on nighttime television, and Kepler was once described as being, raised from the dead or something because it was under threat. So I can't even imagine what our world and your world as professionals would be if we didn't have, at least those instruments and developing and building on them for the future generations. And so I wonder if you could comment about the role of the decadal survey in terms of informing what it is that we do and the importance of staying true to it even in the face of challenges, because we know that each of these programs is very, very complicated and they will face significant challenges, and it's sometimes tough for us on this side to really understand that we've just got to weather those challenges. So that's like a freebie, anybody who wants to take it.
I can go first because I am very proud of that process, so much so that my project in the last decadal survey was ranked number 4 in one panel and didn't make it to the end. So I got to be chopped. And I still think this is the right process. So, I think we need to always prioritize based on the available resources and also the available technology to be able to be always successful. So we don't want to waste anybody's money, no taxpayers' money. And this is a huge effort within the community. We spend a lot of time trying to tell our colleagues, and I think the format that we set up, which is really, merit-based and having our reviews by colleagues of what we are proposing, a really good way to sort out the priorities, the top priorities for large programs. And some of us that don't get to get their project in have to be conscientious that that was the right process. And I think we have had great success exactly for that, because if we weren't following that, we would be in much harder situation. So I think it's a brilliant process.
I'm pleased to, well, first of all, Representative Edwards, I want to say that I bet every single one of us were kids who laid on the beach and looked up and observed the night sky, and we're excited by it. I'm pleased to say that at NASA, in astrophysics, all of our missions our mission decisions are driven by the recommendations and priorities of the decadal survey. Our large missions are those missions which were prioritized to be done first in the most recent decadal survey, and our smaller missions are selected through open competitions, which was also a recommendation of the decadal survey. And so, by following the decadal survey, we are assured that we are realizing the highest priorities of the science community in addressing the broadest possible range of science.
Thank you. And can you add to that, what is the, and Dr. Ulvestad, if you would comment, what's the challenge of, trying to figure out not just what the priorities are, but trying to project what some of the challenges might be so that we get closer on the money front? Because I think that's where we get held up. And then, and add to that, what are the threats to U.S. leadership if we don't engage in a process right now?
So first, I'll say that we too subscribe very rigorously to the decadal survey in setting priorities for ourselves. And one of the challenges we face, as you alluded to, is that the decadal survey committee has to make assumptions about what future budgets are going to be going out 5, 10, 15 years. And so they give us a program, a set of priorities based on some projection. And as you may know, the decadal survey came out in 2010, right about the time that there were difficulties in the banking community and so on. And so we haven't realized the budgets that were recommended or that were sort of believed by the decadal survey. So a really important part of the decadal survey is that they not give us a laundry list, but that they give us priorities. And that way we're able to adjust to circumstances that are not exactly what they assumed. So decadal surveys should always be aspirational. They should always reach for the stars that we all laid and looked at, and we won't be able to do everything they recommend. But by them recommending a compelling program and by them doing a good job of prioritization, that really is one of the best ways that we can react to budget circumstances that are inevitably different from what they assumed.
My time's up. Thanks, Mr. Chairman.
Thank you. I'd like to now recognize the chairman of the full committee, a gentleman from Texas, Chairman Smith.
Okay. Thank you, Mr. Chairman. Let me direct my first question to Dr. Hertz and Dr. Wright. And it seems to me that one of the most promising fields of discovery right now may be detecting optical transmissions from other worlds. And I was going to ask each of you if you could give us an update on what's going on in that field and what our hopes are. And Dr. Hertz, if you'd like to go first.
Well, I'm going to defer to Dr. Wright, as this is not an area that NASA is currently pursuing, and I don't consider myself an expert at all in this area.
Okay. Well, one, I regret NASA's not pursuing it, but Dr. Wright?
I think I can talk, I spoke a little bit about the programs on the optical SETI and the infrared SETI front. Radio's had, 50 years to get a stronghold in the SETI community, while I would say the optical SETI community, or laser SETI in particular, is still in its infancy. We're still trying to make use of the technology that's on hand. There are many things that we can do, and there are many scientists that are interested in doing data mining on all the astronomical data sets that are already there, from the Very Large Array to the Arecibo to Hubble Space Telescope, even Kepler. And that involves getting software engineers involved, other astronomers to think creatively about how they can actually go in there and data mine unusual signals. And so one promising area where people want to move to is look at existing data sets and try to see if we can get optical transmissions. We are also, our team and others are designing a new all-sky, all-time optical SETI and infrared, wide-field infrared SETI experiment, which we're seeking funds to. And we have a meeting coming up in August to go talk about the next phases for this.
Okay. Thank you, Dr. Wright. Dr. Ulvestad.
So I just wanted to mention, we talked about the Large Synoptic Survey Telescope earlier. Yes. That telescope will see of the order of 10 million transient sources per night. That is a source that isn't there in a catalog, but is brighter or fainter or wasn't there at all. And I think given the power requirements of lasers, people aren't going to be pointing their lasers to us all the time. So when that telescope comes up, I think its ability to survey large parts of the sky rapidly and compare them to existing data sets will be very powerful, but it will require the kind of data mining that Dr. Wright just referred to understand what might in fact be a laser-related signal.
Okay, thank you. Actually, my next question was for you, Dr. Ulvestad, and that is, what discoveries do we expect in, say, the next 5 to 10 years when it comes to exoplanets?
So there's a couple things that I expect we will see over the next few years. I mean, discoveries by their very nature are not easily predictable, but we build capabilities and we can sort of understand what kinds of discoveries those capabilities can be sensitive to. So one is that with our partners at NASA, we're working on this very high-resolution spectrograph that will go on a telescope in Arizona and be able to measure masses of planets similar to the Earth. So I expect we will get specific mass measurements of some more Earth-like planets from that over the next 5 to 10 years. A second is that with our Gemini Observatory, we have an instrument called the Gemini Planet Imager, which enables us to image planets like Jupiter in Jupiter-like orbits around stars and actually to get low-resolution spectroscopy at the same time. So I think we'll be learning more about the atmospheres of some of the extrasolar planets. And those observations will drive theoretical understanding of formation and evolution of planetary systems.
Okay, thank you. And Dr. Olinto, is there sufficient coordination between NASA and the National Science Foundation when it comes to astrobiology?
I think the answer is yes. And I was at the AAAC as a member in 2003, 2006, and at that time, I don't think the two gentlemen next to me, the equivalents, would have each other's cell phones. And before the testimony today, we were joking that they could exchange and give each other's testimony. So I think that the coordination has been really wonderful. One of the things we are looking into in terms of the coordination is near-Earth objects, because LSST has a capability, per the Decadal Survey recommendation, to search for near-Earth objects, which is a mandate for NASA to implement. So these things will need to be coordinated too, so we're looking forward to that upcoming coordination between the two.
Good enough. Thank you. And Dr. Jones, thank you for the invitation to the conference. Since I represent part of Austin, I will be there next June.
Thank you. We will welcome you.
Thank you. Yield back, Mr. Chairman.
Thank you, Mr. Chairman. I now recognize the gentlewoman from Oregon, Ms. Bonamici.
Thank you very much, Mr. Chairman, and thank you to all the witnesses. We really appreciate your expertise. I want to ask you a little bit about international cooperation, which is something that we discuss a lot in this committee. Dr. Hertz, I understand that NASA was not able to lead the large-scale X-ray and gravitational wave missions recommended by the Decadal Survey. What is the status of the NASA partnership with the European Space Agency on the Athena and L3 missions, which will address those areas? And I wonder if you could talk a little bit about how important it is for the U.S. to be involved in those missions. And also, I want to bring in Dr. Wright, because you mentioned something about the FAST telescope and the SETI work. And can you talk about the potential for collaboration while we still need to, of course, maintain our U.S. leadership? Are there some areas where we're competing rather than collaborating? Dr. Hertz.
Thank you. That's a great question. Love to speak on that topic. Probably 80% of all of NASA's astrophysics missions are international partnerships, which is virtually all of them, and all of our future large missions are envisioned to be partnerships with our international partners. In order to make the kind of breakthrough discoveries that we look forward to in the future, it requires large and therefore expensive observatories in space, and we're beyond the place where the different space agencies want to put up competing and similar observatories. So we are constantly coordinating with each other on what our future plans are and looking for opportunities to partner. The James Webb Space Telescope is a partnership between the U.S., the European Space Agency, and the Canadian Space Agency. We are in discussions with a number of space agencies about partnerships on the WFIRST Observatory for the 2020s. We have talked to the European Space Agency about partnering on their next two large astrophysics observatories, the ones that you mentioned, the Athena X-ray Observatory, and we have a very mature understanding of what NASA is likely to contribute to that observatory as it goes through the European process of being approved. And then further out in the future, the Europeans have made a decision to lead a space-based gravitational wave observatory, which is a high priority of both of our communities. We have expressed a strong interest in partnering in that. We are engaged in discussions about what our role might be, and we have been for the last number of years investing in technology development here in the United States to make sure that we have developed unique technologies that we can bring to such a partnership and make a U.S. Involvement in such a observatory a win-win for both partners.
Terrific, thank you. Dr. Wright, on the SETI work, is there room for collaboration?
I'll comment on the FAST telescope in China. There is a collaboration going on with Berkeley right now to help with the receivers. So as I said, the dish is already made, but they have to work on the electronics and the antenna to actually detect it. There is the frequencies for which they cover are slightly different than Arecibo. So there's there's competition on particular frequencies, but on others there are not. And it's not clear to me yet, or I don't think I could comment on whether the Chinese scientists want to collaborate with the SETI work and how we would work together within it. I'll also add just one statement that a group in Italy has been trying to push on optical SETI and trying to collaborate with us and get our understanding of the technology there as well.
Terrific. And Dr. Jones, I want to ask you, in your prepared statement, you note the importance of making observations publicly available no more than a year after they're obtained. So can you elaborate a bit on why that's so important to advancing the science, and perhaps following up on Ms. Edwards' questions about how we talk with our constituents and the public about why it's important to invest in astronomy and astrophysics and science, especially with long-term planning that's so needed, might making observations publicly available help in communicating the value of your work with the public?
Sure. I mean, the archives are tremendously important, not just to astronomers, but to anybody who wants to look at the observations. There are large archives of the Hubble, of the Chandra, of all of the major missions, as well as the ground-based missions. NOAO has archives of the 40 telescopes, I think, which are archived since 2004. And NRAO also has large archives of the radio observations.
Just in the remaining time, are there some examples of where observations conducted with federal funding are not made publicly accessible and available?
No, I think they're all made accessible on a time scale no longer than a year. Some are made sooner, but it's tremendous research. So much of what people have discovered, they've discovered from the archives, not because they were looking to propose to do something, but they find it in the archives.
Terrific, and I see my time has expired. I yield back. Thank you, Mr. Chairman.
Thank you. I now recognize the gentleman from Oklahoma, Mr. Lucas.
Thank you, Mr. Chairman. And Dr. Wright, when the general public focuses on SETI, we live in a time where it wants immediate gratification, things happening right now. But in some ways, isn't this kind of like a junior high dance? We've been making noise now on this planet since Mr. Marconi, century probably. So the noise wave is, 80, 90, 100 light years out? If you're past that point, then there's no indication that we're here to the rest of the universe. Fair statement? Therefore, part of the challenge of finding something is someone looking for us too.
One of the interests for NASA missions and NSF missions are for extrasolar planet atmospheres. So there are other means to detect whether there are biosignatures in the atmosphere to know whether there's life there. So they may know we're here, whether they're beyond listening to I Love Lucy 90 light years out. But we're just still in our technological infancy, right? We're
exactly the point I was trying to make.
So the standpoint for SETI is that hopefully we maintain our technology and civilizations much longer, and they would be advanced thousands or hundreds of thousands of years longer than us. So they would have other means for this.
Along that line, that means that we have to maintain our basic investments in not just technology but people. But Dr. Wright, to you and Dr. Olinto, discuss for a moment the nature of the astrophysics research programs in American universities. How many are there? How do we compare to 10 or 20 years ago? What kind of facilities they have to work with? That next generation who'll come after all of us in this room, where are we in this country right now?
I think we're doing quite well. I think that there's been no greater interest than for astronomy and astrophysics. The facilities we have many ground-based observatories that we use through universities, small-based facilities that have been excellent for trying to test innovative new instrumentation on, which is very important before we bring them to larger ground-based telescopes or we give them to NASA to put on space-based telescopes. There's heavy student involvement, and in fact, the enrollment is even higher for astrophysics bachelor's degrees. Those programs have spread through academia. And there's a greater interest within a PhD, which I think has already been commented by the panel. A PhD in astrophysics is a great springboard to any of the STEM fields.
Dr. Olinto?
Thank you for that question. I agree, it's really wonderful times, and the number of students and interest is just growing. But as I mentioned in my statement, one of the challenges of flat budgets is that the facilities which we really love to build and want to use do keep growing because, they have to be constructed, operated, there's inflation. So it's much harder to protect the grants program and the mid-scale program, which is where the new ideas and the new people get formed. So this is the big challenge right now in trying to make sure that the future will be as wonderful as the present, is to really find a way to protect this most flexible part of budgets, which is the individual grants program. And I was just visiting her institution, and on the board there is the plot that we wrote in the AAAC with the proposal pressure going high. I mean, the pressure is so much higher that much fewer grants are being able to be funded. So I think this is the challenge we are facing now, that we should keep an eye on that, because it obviously doesn't come in as a flagship mission. It's always sort of the small programs, but those are really where the new blood comes in.
But you're confident the blood exists if the resources
definitely.
Available are there for them to do their work.
Exactly.
Does exist.
Yes.
Dr. Hertz, you mentioned the 9 Earth-like planets so far. What's the range in light years away? Closest to farthest, just rough numbers.
Yeah, I certainly don't know that off the top of my head. I'll be glad to take that question for the record and get back to you.
That's a fair response. Thank you. Yield back, Mr. Chairman.
Thank you very much. Now I'd like to recognize the gentleman from New York, Mr. Tonko.
Thank you, Mr. Chair, and welcome to our panelists. And this is a question for any of you, can you characterize the current representation of women and minorities within the astronomy and astrophysics communities?
I can start with that. The numbers are growing, but the numbers are still very small. Having 3 of us here does not represent that there are a large number of women in astronomy. But the numbers are growing. The number of underrepresented minorities is not as large. We've had an RAU program at Smithsonian for the last 20-something years. I've been PI of that. We take 10 students each year. This last year we had 300 applications. We've always had at least half of them are women. And we have a few, not as many as we'd like, of underrepresented minorities. But I think those NSF programs are tremendously important for bringing in women and underrepresented minorities.
To any of you, and yes, Dr. Ulvestad, is there something that can be done in a targeted way that will improve those numbers?
Yeah, so I'm not an NSF lifer. In my pre-NSF life, I chaired the Decadal Surveys Demographic Study Group, and Dr. Jones was actually a member of it. So I think on the gender side, we see substantial increases in the number of women in the physical sciences and astronomy. I think that the numbers, if you look at the undergraduate level in astronomy, are approaching 40 to 50%. And one of our challenges is that as you get to the higher levels in academia, those numbers tend to get smaller. And so a challenge to us as a society is really how to maintain the interest of the people who are coming in as undergraduates. On the underrepresented minority front, I think the physical sciences in general have not done very well. We have specific programs in our division, in our materials research division in NSF, But I'll point out that NSF-wide, the NSF has just started a new initiative called Includes, and it's a long acronym, I don't remember exactly what it stands for, that's specifically aimed at underrepresented minorities. We recently had our first round of pre-proposals for that and got over 600 pre-proposals that will be winnowed down to full proposals that will be invited. So I think NSF as an institution is trying very hard to sort of get these programs going. I think that one of the issues for NSF is that we can address things at sort of the college and postgraduate level, and a lot of the issues relating to representation start much earlier in careers.
Thank you. And to Dr. Jones and perhaps Dr. Olinto, what's the impact of low proposal success rates on the nature of the projects that get funded? In this high-pressure environment, is there sufficient support for the more long-term investigations that don't have a clearly defined result within a couple of years?
The low proposal rate makes it very hard for people. They're just, when only one proposal in 10 roughly is being accepted, I think it's discouraging. The funds that usually come in because those proposals are successful are usually the ones that support graduate students and postdocs. So it makes that, you can't support as many of the younger people who are coming up. So, it is very, it's hard and it's discouraging for members of the community. In theory, the best science, the very top 10% is still getting done, but much of the science is really excellent and should be supported. So.
Dr. Arlento?
To add to this, it's difficult in many respects, and especially because it used to be 30% and now it's 20%. So the change makes people propose more because they used to get grants. So folks that had support stop having support, and new folks coming in will then have to fight even harder. And what happens is you have excellent reviews that don't mean funding. So when you write an excellent proposal and you get no funding, then you don't know what to do the next year because, how come it can't go better than excellent. So if we leave excellent proposals on the chopping block, that is a problem. If we don't have a perfect number, but historically the 30% seem to have been a very healthy way to keep excellent and very good science and innovative. Because when you're squeezing the excellent out, you're also squeezing the risk, right? Because we know that those three will probably be okay. This one, which takes a little more risk, will not. We probably don't fund that because we don't know, and that's not how science should be done, right? We should really gain from a little bit of high risk investment. Obviously, not all of it of the portfolio. So it's very difficult right now because of this decrease. So anyway, yeah.
Okay. Well, my time has expired. Let me thank you all for participating today. With that, Mr. Chair, I yield back.
Thank you. Now recognize the gentleman from California, Mr. Rohrbacher.
Thank you very much, Mr. Chairman, and thank you to our panelists today. It's been very thought-provoking. I've always supported astronomy. I've been here 28 years, and I buy on and I've bought on to the idea that astronomy helps us with a basic understanding of the universe, not just out there, but down here as well, and expands our fundamental knowledge base, which are two very laudatory goals. But number one, doing this is an expensive proposition, and it's an expensive proposition that benefits all of mankind, not just Americans. And so I was heartened to hear the efforts that are being made on international cooperation, and I think that should be expanded. By the way, I didn't hear any cooperation with Russia. Is our current relations with Russia, which are very dicey right now, is that preventing us from having the type of cooperation in this area that could be beneficial to both our countries?
Thank you for the question. No, I don't think so. I mean, Russia is a very strong partner on the International Space Station with NASA, and we're very pleased to have their partnership on that project.
Okay. Well, that's the answer. Thank you. I'm glad to hear that. I think there's sometimes we need to, when we have adversaries, we need to find ways of cooperating that can actually lessen the tension between people who have different points of view and countries that have different points of view. One of the underappreciated services provided by astronomy and by this area of science that we're talking about is an early warning system that could alert us to objects coming from space that could cause enormous damage, if not the ultimate damage, to the Earth. And that is something that is an immediate payback rather than just expanding knowledge. We're actually getting a warning that could be utilized, which we have not yet put the system in place, to deflect an object that might be coming from space. One of the prerequisites in order to set something like this up, which has been a long project of mine, one of the really assets that we would have is the Arecibo telescope. And Dr. Ulvestad, there's been some statements that you've made that indicate that Arecibo, we were in the initial steps of mothballing it. Do we have other assets that can spot an object that far out and actually chart its course so that if 10 years out there's an object there that would be hitting the Earth? I understand Arecibo provides that service. Do we have other ways of providing that service intact now?
So first I'll say we haven't made any decisions about what the future of Arecibo is. We're studying a variety of options. But in terms of detecting objects far out, what you really need for that is a survey telescope with a very wide field of view, which Arecibo is not. So Arecibo's radar can be used to characterize the properties of an object, say an asteroid, that is already known about that you can point at. But in terms of the NSF investment, the LSST, which can survey the sky and, as we said, would detect...
Is that already in place?
No, that's being built. That will be...
It's not in place, so we don't have something in place that would, if we mothball Arecibo this year, that would be immediately taking over that particular threat and handling that.
Well, Arecibo, as I said, is not a survey telescope, so it can only do radar characterization of asteroids that are already known about. So
radar calculations, by the way, of where it would actually threaten the Earth.
No, what they actually do is they do radar assessments of what the composition of the object is, because if it's like a rubble pile versus a solid iron mass, it will have a very different impact.
But does not, the Arecibo telescope is not involved with charting the actual potential of an object to hit the Earth?
It's involved with tracking it. The tracking can also be done with optical and infrared telescopes.
It could be done.
Yes, and is done.
Is being done.
Yes.
So if Arecibo, so your testimony today is that Arecibo is not providing at this time a service that is not all being provided by someone else.
So as I mentioned, the radar characterization is unique to Arecibo, the characterization of the properties of an asteroid.
Right.
Now, NASA also has a radar at Goldstone, but that's a smaller dish, so its reach into the distance is not as far.
Right. So the actual being able to determine, as you say, what the composition is not something that tells us whether or not that is a threat to the Earth?
It tells us something about whether it's a threat to the Earth. I think that it doesn't tell us uniquely about its path.
Okay. Well, Dr. Hertz, could you give us your answers to that?
Well, I certainly agree with everything Dr. Ulvestad said. He mentioned the Goldstone radar that's part of our deep space network. It's also used for radar characterization of asteroids, and unlike Arecibo, it can be pointed. Of course, Arecibo cannot be moved, sitting in a valley the way it does.
and Dr. Olinto, do you agree with?
Yes, I think there are many survey telescopes that are working now, Pan-STARRS, Dark Energy Survey, other survey telescopes of the type that LSST will be the primary. LSST will be another huge next-generation improvement on what we already have. So there is a menu of things that one can do, but LSST will certainly add a huge amount to this issue.
Yeah, now, again, I'm really looking at, and Mr. Chairman, what's important is not what we are planning to do, but what we have. And quite often, for example, when I was chairman there in your seat, we passed a bill called the Pete Conrad Astronomy Awards Act, which gave people awards for discovering the biggest Earth object out that might threaten the Earth. And, you know, that it's just a very small amount of money, but that's never been you know, we've never appropriated the money for it. So it's one thing to have a plan and say, well, Arecibo won't be needed because we've got this other group telescope and it's on the way. Until it's there and until it's appropriated and actually put in space, we have to calculate on what capabilities we have at this point. And while I agree with you, and the decadal studies should show what's important, what's really important is making sure our Earth isn't destroyed by some space object and all of us die. And if there's any other priority, I think that would have to be the top priority. And we need to make sure that we don't have holes in the system as we're planning to put something up. Let's make sure we keep Arecibo and other assets until those alternatives are in place.
Thank you.
Thank you, Mr.
Thank you. Gentlemen's time has expired. Okay, Mr. Byer from Virginia.
Thank you, Mr. Chairman. And, you know, America's had a sad week, a rough week. So thank you so much for coming here with so much optimism and so much energy, so much belief that we're doing a lot of things really well. By the way, I have two of my interns here today, Alexa and Max. But I bring up Max because his favorite movie is Interstellar. So he's thrilled to be here. So, Dr. Wright, Fred Drake, 1961, came up with the famous Drake equation that was going to predict how much intelligent life there likely be in the universe. That was before we had all these very cool telescopes. Based on all the research we've been able to do, you know, are looking much deeper into space. How has that equation changed? What does it predict now?
So I think the key one, especially back at that time, was understanding the number of extrasolar planets. At that time, it could have been 1 in a million, or it could be 100%. We actually had no idea. And with this increase, we basically have a 22%, right? It's 1 in 5, that says every sun-like star has another Earth-like planets. I always tell the students, count in fives. Go up and count 5 stars. There's another Earth-like planet staring back at you. That's huge. But as Carl Sagan pointed out in the Drake equation, it's L, it's the lifetime of a civilization that really makes the big factor on the number of communicating civilizations. And so really it's how long a civilization may last. The lifetime of the universe is very long, billions and billions of years. Life here on our planet's been here for 3 billion years, but our civilization's only been here for 10,000. So it's a sliver of time. SETI takes patience and diligence and understanding and projecting where our technology will go.
Great. Thank you very much. Dr. Jones, I've always been fascinated by the oscillating universe model. It's going to expand until it gets, and then it will contract. But now that we know that the universe is accelerating, what does that suggest for the oscillating universe model?
I think it will probably, this will be a one-way trip. We will be expanding and we will not be collapsing again. So, sorry, it's not, it's sort of not the optimistic view, but.
So we're back to linear time then?
Yeah, afraid so.
Darn. Dr. Hertz, were you born to be a physicist with that name? Or?
Either that or a car rental agency.
So, Dr. Hertz, one thing I haven't heard today is whether we're making any progress on understanding why matter in the universe is so asymmetrical. Why is there so much more matter than antimatter?
Yeah, I'm going to pass that to Dr. Olinto.
All right.
Because that's
Okay,
one of her areas of
I'm
research.
itching to reply. So that's a very hard question. Why there's matter and antimatter in this room, and we're very lucky that that's the case. Otherwise, we wouldn't be here because matter and antimatter annihilate. And this has to do with fundamental physics, which a previous member also mentioned. And I think that is why these broad, this large piano that we use can address issues that relate to the early beginning. So one of the big questions is, how did gravity separate from the other three forces, and how that process, which we is beautiful to talk about, with family at parties, but it's also something we can measure. And so that's, to me, the most exciting part. So many answers to the questions, the fundamental questions you're having, have to do with, what is dark energy, including the future. If the dark energy decays, we might heat up again, so we can choose fire again, maybe, between fire and ice. But the early moments of the universe we can address by looking at the microwave background. And this is one of the many areas of research that the portfolio of the Decadal Survey is considering and also investing on. And it is an interagency, both NASA, DOE, and NSF, the three agencies we oversee, are investing very heavily on looking at these primordial microwave background patterns. By looking at the polarization of this light, which comes from the Big Bang, we can tell some properties of gravity at the time. And then that will connect to the fundamental physics that separated matter and antimatter, for example. So it's all a very interesting pursuit also.
Is all this tied together, Dr. Olinto, while you have the microphone? Because you're looking at dark matter also and dark energy.
Right.
All related?
We don't know. So we don't know. We have a very good way to try to detect dark matter directly, and this is a huge effort. DOE and NSF are involved. Dark energy, we are measuring as well as we can. It's much harder to detect. It would be easier if we could get out of our universe, then we could measure it from the outside. But being inside it is really, really challenging. There are theories that connect the two, and that would make sense since they're two unknowns. Maybe they have something to do with one another. But it may be that nature, just like in exoplanets, are much more creative, and we don't really know the answer.
Great. Thank you all very much. Mr. Chair, yield back.
Thank you, Mr. Byer. Now I recognize a gentleman from Illinois, Mr. Holtgren.
Thank you, Chairman. Thank you all so much for being here. Thank you for your work. And this really is an exciting and important hearing for us all to learn about and hear about the state of astronomy, astrophysics, astrobiology research in the United States and also internationally. These are certainly some of the toughest fields, requiring the best and brightest to devote lifetimes to their field with no guaranteed or big economic payoff. It takes a passion, and it's inspiring for me to watch your work, and want to thank you for your work. In the committee, we will certainly continue to follow the recommendations of the Decadal Survey, and there are countless big ideas or future projects we could be discussing, but we all know that none of this can be ever even possible if we're not inspiring the next generation to follow in your footsteps. Often that takes just a small spark in a young person's mind, maybe a burning question, a first telescope, a robotics competition, simple reassurance from a parent, a friend, or a mentor that this is something you can do, and we need you to do it. So I want to just ask, and I've asked this before in other committee hearings, but I'll start with Dr. Jones, and maybe if we can just kind of go down the line. It's helpful for me because you certainly are some of the best and brightest in your field, but I've noticed for experts in the STEM field that there's no single pathway to get to where you are. So just some simple questions. Wonder if you have any thoughts. When did you know that this was something you wanted to do? Who inspired you? Feel free to give a quick shout out to a teacher or mentor. They always could use the credit and recognition. So if you could maybe just let us know kind of your path, if there was someone that inspired you and what it was that maybe first sparked that idea that, hey, this is something interesting and something I could do.
I've been lucky to have a number of mentors. I think I grew up near Dayton, Ohio, and there was an honors. Everybody likes Dayton? Good. And good. There was an honor seminars of Metropolitan Dayton, and I went to that. We had weekly lectures. Kids from different high schools came in. And for me, some of the most exciting were on then neutron stars, these spinning pulsars, and the lectures were given by scientists at Wright-Patterson Air Force Base. And I worked when I was in college. I worked for a summer or two with somebody at Wright-Pat for those summers, and it was terrific. So that's how I started.
Dr. Wright?
I think I knew as a little girl that I was addicted to the stars and the universe and trying to understand it. Probably the most formidable experience was in middle school. In my science class, they decided to play the Cosmos series by Carl Sagan, and I was hooked by watching those. And then I, too, have had many mentors, thankfully. When I went and did my physics degree at the university, I had exposures to telescopes, scientists, instrumentation, working in labs, and I think having that hands-on experience was vital for me.
I started more interested in physics than in the universe because understanding how things move, how things drop, and the basic laws of physics to me was so much easier than human beings. But very soon after getting interested in that, I realized how the universe is the best place to actually learn more about physics because it has all kinds of systems. It takes everything to the extremes. So it's been a wonderful path. And I have many other interests in high school, but certainly high school teachers were really important. Also, my parents. My father always challenged me for all kinds of math quizzes. And the Cosmos series, which I aired in Portuguese in Brazil. So the outreach is really broad in that sense. So I thank for all this production that happened here. And also the Apollo missions made a big impression for me as a kid.
So I was really good at math, and when I was in high school in my physics class, not knowing what I wanted to do, we had, I remember, a visiting professor from the University of Southern California, and it pains me to say that as a UCLA graduate, but that professor came and talked to us about cosmology, and that got me really interested in astronomy. And then I took advantage, in Los Angeles, they have something called the Griffith Observatory, which is in the largest public park in LA. And you can't imagine that you can see much of a dark sky from Los Angeles, but they had educational programs and a planetarium, and that really got me excited so that when I went to college, I majored in astronomy.
That's great. Thanks. Dr. Hertz.
Well, I was a child of the 60s, and I grew up just loving to read about all the NASA missions that were going on. My father, we lived in Atlanta, and my father gave in to my love by driving us down to the Cape before the Apollo launches, and we would camp out on the beach and wake up the next morning and watch them blast off to the moon, and so that set my path.
That's awesome. Well, again, thank you all for your work. We appreciate it. Thanks for inspiring others as well. That's so important, and that's our only hope, truly, is for our young, best and brightest to be willing to follow in your footsteps. So thank you all, and I yield back.
Yes, sir. Very fascinating. Thank you. Let's see. I now recognize the gentleman from Colorado, Mr. Perlmutter.
Thanks, and I just love those questions Mr. Hultgren asked and your answers. I mean, this is like coming to super science class for me, and I'm so surprised by my colleague here, Ambassador Beyer, and all that he knows about science. You know, me, I watch Star Trek, so I think about the next generation's a character, the traveler, so the time traveler, or the Q continuum, you know, all powerful, whatever. Or Heinlein, you know, talking about multi-dimensions and multi-universes so that you actually could be in a different time frame looking at our universe. And I'm just so speechless by all of your testimony, and I just thank you for being here, and I thank you for your optimism and your willingness to research and look into the future, because that's what this is about. So I'm going to ask you a couple of specific questions, but you really have brightened my day, and I thank you for that. Space weather. Dr. Ulvestad, let's talk about space weather a little bit. I am working with Congressman Molinar and a couple of the senators on space weather legislation. I guess my question is, we had Dr. Baker from the University of Colorado, so I'm obviously from Colorado, and we've recently been assigned by the NSF the National Solar Observatory, and we do a lot of space weather and space activities in Colorado. Can you tell us how the space weather future looks?
So some of the members may know that we've recently developed a national space weather strategy and a space weather action plan, and that was an interagency activity that involved NASA, NSF, not just the science research agencies, but also people who might have to respond to space weather outbreaks and get early warnings out, such as FEMA. So that, I think, was a really interesting process to develop this space weather strategy. As part of the space weather strategy, NSF actually has some deliverables. So there's the long-term research aspects, and so I showed a picture of the Daniel K. Inouye Solar Telescope earlier, where really understanding the fundamental magnetic processes in the sun will be critical to us for eventually being able to predict space weather. I'm not going to guarantee that, but understanding the sun means 10, 20, 30 years down the road, we may be able to do better at that. And early warning systems enable satellites to shut down and point in the right direction and so on, so they're not damaged. Operationally, we right now run something called the Global Oscillations Network Group, which is run by the National Solar Observatory that, as you pointed out, is relocating to Boulder. And in our 2016 budget, in our request, we added money to make that a more robust system for predicting space weather. It's a network of 6 telescopes spread around the world so that it can, assuming it's not cloudy, observe the sun 24/7. And its data are actually used by the Air Force for operational space weather prediction. So I think we have a mix of both an operational role where we're taking some of our research capabilities and transitioning them to operations, and also the long-term research role.
So I just spoke at a seminar and symposium on cybersecurity, and we were talking about electromagnetic pulses. So, you know, potentially man-made, but more likely something coming out of the sun, that a flare of some sort that just fries, you know, our communications grid, our electrical grid, or whatever. So I hope, I mean, obviously that's what you're talking about in terms of the operational assistance that NSF is giving.
Yeah, so the NSF role in that is primarily the research role. We don't have FEMA's job, and we don't have the DOE job of sort of maintaining the electric grid. So our goal is to be able to produce the research that will enable us to do better predictions in the future, and the issue of like hardening the electric grid is kind of out of our realm.
Just a closing thought, and Dr. Hertz, I had a bunch of questions about this space shade that might help our telescopes, but I just want to congratulate the astronomers and the astrophysicists on, and somebody may have done this before I got here, on getting to Jupiter within 1 second, and the engineers and the mathematicians and the technologists and everybody who helped on that. And my only question is, how are we off by 1 second? That was rhetorical. I'll yield back to the chair.
Thank you, Mr. Perlmutter. Now I recognize the gentleman from Ohio, Mr. Davidson.
Thank you, Mr. Chairman. Thank you all for being here. Thanks so much for the encouragement and just an impressive amount of information. Growing up near Dayton, Ohio, near Wright-Patterson Air Force Base, one of the first field trips I took was to the Neil Armstrong Space Museum as a kid. And so it's long been an interest. And I found that I would not be able to pilot any of these aircraft, so I might just jump out of some of them. So here in our orbit, though. Turning away from, not to take anything away from all the great science we've just talked about, I want to talk a little bit about the science of project management. And so, Dr. Hertz, you mentioned about the JWST program, and for 2016, the goal is to have the 3 main components, the scientific instruments, the telescope, and the spacecraft completed. Is that project on track?
The James Webb Space Telescope project is on track. It is executing the replan that was laid out in 2010, and for which Congress, thank you, has been appropriating the right amount of money in each year to allow us to make progress against that plan. We have not accomplished the things that you listed, but those were not planned for 2016. Those are in 2016, we've assembled the telescope and the instruments together, and the spacecraft is being assembled separately in California. The telescope and instruments are in Maryland. The spacecraft is in California. At the end of next year, we will be shipping the telescope and instruments to California to be mated with the spacecraft.
Okay, thank you.
But we are on plan with our, on track with our plan.
Okay, thank you. Dr. Ulvestad, the telescope under construction in Maui, so thank you for the physical picture of it. It looks great, still in progress, but a bit over budget. Inspector General issued an alert warning for further cost and schedule risk to the project. I'm just curious, what steps has NSF taken to address the concerns, and how confident are you that you will meet the new project deadline and budget?
So we're actually quite confident that we're on budget. So that telescope was rebaselined to a new budget in 2013 because there was a 2-year delay in access to the mountain due to environmental and cultural permitting issues in Hawaii. So the Inspector General report made several recommendations. One of the concerns was that the schedule was, the project schedule was working toward a completion in late 2019, but it was always known that that was the schedule without the risk associated. That was the schedule that had a 6% probability of being met. Okay, the schedule that had an 80% probability of being met was the middle of 2020, June of 2020. So we are quite confident that we're on schedule to meet that 80% date and actually to do it within our current baseline budget.
Great, thank you. I have a question, again, Dr. Hertz or any others that want to comment. NASA is funding 4 large mission concept studies that will inform the 2020 National Academy of Sciences Decadal Survey. NASA anticipates that the survey committee will use these studies in formulating the recommendation for the priorities of the missions following JWST and WFIRST. What does NASA intend to learn from these large concept mission studies, and how may these studies influence the upcoming 2020 Astronomy and Astrophysics Decadal Study? Are these studies intended to influence the Academy's review process?
Thank you for that question. These studies are to put in front of the Decadal Survey Committee some options for prioritizing for missions that come in the next decade. So each of these studies, the study teams are made up of scientists drawn from across the country. Each of the studies will lay out a science case to lay out what amazing science could be done with that particular mission, to lay out a notional architecture, how big a telescope, what temperature, what orbit, what cameras, that sorts of thing. And then we'll let the engineers take a look at it, and they'll estimate how long it would take to build and how much it might cost. And that package that describes what such a mission might do and what kind of resources it might take, that can be put in front of the Decadal Survey Committee, and they can consider those as possible future missions, or they can consider anything else they wish to consider as a possible future mission.
All right, thank you. Mr. Chairman, I yield back.
Thank you. Thank you very much. I want to thank the witnesses for their very valuable and fascinating testimony, and for the members up here that have asked great questions. The record will remain open for 2 weeks for additional comments and written questions from members. And so with that, this hearing is adjourned.